A research collaboration manages data collections, analysis workflows, and data flows. For collaborations that involve multiple institutions, the collections, workflows, and data flows are distributed across multiple locations. Data grids provide the namespaces for uniform naming of files, workflows, and users, for organizing the files into collections, and for metadata management for description and provenance information. A research collaboration forms a consensus across the team members for how the collections will be managed. The team members may implement personal collections while they are developing their analyses, project collections that contain the collaborative results, shared collections that are exchanged with other projects, and published collections that are made available for their entire discipline. Each collection may have its own control policies, its own retention policies, and its own metadata. The same types of properties apply to workflows that apply to data collections. A research collaboration needs to identify how the workflows will be named, the provenance information required for each workflow, how the workflows will be shared, and how versions are created when workflows are re-executed. Workflows can be described in the iRODS rule language and saved as a text file. The reason to track workflow provenance is to enable reproducible research. A second researcher should be able to reproduce the results created by the first researcher. If a workflow is modified or input parameters are changed, the new output results can be compared to the previous analysis. This requires the ability to version both the workflows and the result sets from the execution of the workflow. The analyses applied to data sets are as important as the results that they generate. Workflow result sets should maintain strong links to the input data sets that were analyzed. Data analyses may require the movement of data collections to a compute resource where the analyses are performed, such as computation provided by a remote web service. The opposite movement is also possible with the movement of an application to the location where the data sets are stored. The application can be encapsulated in a machine image that includes both an operating system and the application. The machine image can be run in a virtual machine and access data sets locally. The data or application movement is a data flow that maps the data movement from the source locations to the destination. Data flows should be named and described. Their characterization should be saved as a text file. Data flows should be shared, re-executed, and versioned. Policy-based networks, such as software-defined networks, will eventually have the ability to manage data flows. Movement of terabytes of data and millions of files through a secure network is a data flow example. Research collaborations have the need to characterize and manage data collections, workflows, and data flows independently of the choice of technology. Current data grid technology can virtualize the properties of data collections and workflows. The virtualization of data flows is a research goal. Data grids such as iRODS are being integrated with software-defined networks to start virtualizing data flows. The NSF Syndicate project is one of the initiatives that is integrating data flow management with the internet. Please take 7 minutes to do exercise 8. Write a paragraph on a design for a collaboration. Define a collection you will need. Define policies or workflows you will need. Define data flows or data movement you will need. Please load your paragraph into the Lifetime Library in the sub-collection class INLS 624 by the end of today's class. The DataNet Federation Consortium is a National Science Foundation funded project to implement national data cyber infrastructure through the Federation of Existing Data Management Systems. The participants include the University of North Carolina at Chapel Hill, the University of Virginia, Drexel University, Arizona State University, the University of Arizona, and the University of California at San Diego. The DFC vision is to enable reproducible research. A second researcher should be able to reapply the analyses on the original data sets and verify the research results of the first researcher. This has multiple implications. The researchers can participate in collaborations, sharing not only data but also workflow analyses. Reproducible research will require management of workflows, including tracking of workflow provenance. And each researcher should be able to implement policies related to management of their analyses. A national infrastructure will facilitate interactions between researchers. The DFC is conducting research on federation mechanisms, including the design of new interoperability methods. Since standards and protocols will continue to evolve, a national infrastructure will need to be highly extensible and incorporate new technologies as they become available. The DFC addresses this problem by using policies to manage interactions with technology while managing both data collections and workflows. The DFC is itself a federation of 6 national scale research projects. Each research project serves a different discipline, has unique policy requirements, and serves a national community. The disciplines include hydrology. In collaboration with the HydroShare project, watershed hydrology analyses are being turned into workflows that can be automatically executed. Marine Science Observatory Network, real-time sensor data streams from environmental, seismic, and oceanographic sensors are analyzed, shared, and archived. Engineering, engineering ontologies are created to build reserved vocabularies for describing materials. Cognitive science, researchers form collaboration networks on joint research initiatives, and the collaboration networks interact to address discipline-wide research questions. Plant biology, teams of researchers apply community-developed tools to analyze plant genomics, publish results, and share data. Sociology. The Dataverse Research Data Management System is being federated with the DFC to support alternate archival storage mechanisms. A federation hub enables interdisciplinary collaborations. In practice, the most notable sharing is through repurposing of clients, analysis tools, and policies between disciplines. A major challenge in the generation of a watershed hydrology analysis is the acquisition of a wide variety of datasets from federal repositories, the projection of the datasets to the region of interest, and the tracking of this provenance information for each execution of the analysis. It is not uncommon for an analysis to require the manipulation of 3,000 datasets. Agency repositories that are accessed range from NASA to NOAA to the Department of Agriculture to USGS to the Department of Transportation. The DFC provides interoperability mechanisms to enable the data retrieval, provide support for workflow execution to do the required transformations on the input data, and provides the provenance mechanisms to track which datasets were used by which analysis. The DFC has observed the existence of a community-based collection lifecycle. A dataset in isolation is of marginal use. Instead, a context is needed for each dataset that provides provenance information, descriptive information, and assurances that the data are trustworthy. The DFC uses collections to define the context for datasets. A notable observation is that collections have a life cycle, as shown here. A project may assemble a local collection shared by team members. Each member has complete tacit knowledge of the naming, arrangement, description, and provenance of each dataset. When the project shares data with other institutions, the tacit knowledge must be made explicit through the creation of appropriate metadata. Policies are needed for access control and distribution. If a processing pipeline is created, the knowledge needed to understand how to manipulate the datasets must be captured as workflows. When the collection is formally published in a digital library, the descriptive metadata and arrangement will need to correspond to discipline standards. For the formation of a reference collection, a knowledge community must be defined that will be able to interpret the collection in the future. If the collection is federated with other collections, then policies will be needed to control repurposing and reuse. These transitions are managed by establishing extended management policies to meet the requirements of the broadened user communities. A collection lifecycle is virtualized through policy evolution. Policies are used to control interactions between each of the participating communities. The policies may be specific to a discipline, such as metadata extraction or intellectual property rights or data analysis. Some policies are generic and used by all disciplines, such as authentication and authorization and integrity. Policies may also be specific to the stage of the collection lifecycle. Thus, the social science collaboration is very mature and focused on reference collections. The cognitive science collaboration is very new, with a focus on helping researchers build collections. By using extensible technology, each community can manage evolution of their data management systems to support future needs.